Did you know that flipping the bits of a number, literally reversing them, is a favorite falling interview question? Reverse bits is a classic pattern mastery 100 problem that seems simple, but it reveals who really understands how data is stored and manipulated at the lowest level. Master this, and you'll unlock a new level of confidence for bitwise questions, data encoding, and optimization. Let's break it down. Given a 32-bit unsigned integer, reverse its bits and return the resulting integer. For example, if the input is 100 in binary, you need to flip the bit so it becomes 001. Let's assess our approach. The brute force way is actually perfect here. Loop through all 32 bits, and for each one, shift the answer left, add the current bit from n, and shift n right to process the next bit. This runs in 01 time, since 32 is constant, and 01 space. Here's the structure. Initialize result to 0 for 32 times, or as many as the number's bit length. Shift result left by 1 to make space for the next bit. Add the least significant bit of n to result or equals n and 1. Shift n right by 1 to process the next bit. When done, return result. Let's try to implement it using solution 1. We start by defining a class called solution. This is simply the container where we will place our method for reversing the bits of a 32-bit integer. Here we define our method, reverse bits. It takes a 32-bit integer n and returns another integer where the bits of n have been completely reversed, like flipping a digital barcode from left to right. We initialize a variable called res, starting at 0. This will gradually become our reversed number, built one bit at a time. This begins a loop that runs exactly 32 times, once for each bit in a standard integer. Since the loop always runs a fixed number of times, the time complexity is 01, constant time. This line performs the core of the bit reversal. Res1 shifts all bits in res to the left, creating space for the next bit. N and 1 extracts the last bit of n. If the last bit is 1, this becomes 1. If the last bit is 0, this becomes 0. The operator, bitwise OR, attaches that extracted bit onto the rightmost side of res. This line shifts n one bit to the right using the unsigned right shift. Unsigned means we always fill the new leftmost bit with 0, no matter what the original sign was. This effectively removes the bit we just took and moves the next bit into position so we can process it on the next iteration. We return res, the fully constructed reversed bit integer. And that's how this algorithm works. It first initializes an empty result, then repeatedly extracts the last bit of the input number and shifts it into the reversed output until all 32 bits have been processed. Solution 1. Test case 1. Let's test our function using this input, 43,261,596. This number represents a 32-bit integer whose bits we want to reverse, meaning the leftmost bit becomes the rightmost, the next becomes the second to last, and so on. When we reverse the bits of 43,261,596, the algorithm works through all 32-bit positions. It takes the last bit of n and appends it to the result. Then it shifts the result left to make room for the next bit, and shifts n right to read the next bit. This repeats 32 times until the entire bit pattern has been flipped. After processing all bits, the reversed binary pattern corresponds to the decimal value 964,176,192. And that's exactly what our program outputs, 964,176,192. And the expected result matches perfectly, 964,176,192, confirming that the bit reversal logic is functioning exactly as intended. So, our implementation is correct. The algorithm successfully reverses all 32 bits using simple bitwise operations, efficient and accurate. Now let's try another implement approach using solution 2. We begin by defining the solution class, the container that will hold our more intuitive, string-based method for reversing bits. This method, reverse bits, takes a 32-bit integer and returns another integer whose bits are reversed from left to right. This line converts the integer n into a binary string. Here's what happens step by step. Integer dot to binary string n converts the number into binary, but may omit leading zeros. String dot format %32s pads the binary string so it becomes exactly 32 characters wide. Dot replace comma 0 fills in all the padding spaces with 0, ensuring we get a full 32-bit representation. In simple terms, we take the binary number, fill in missing zeros on the left, and get a clean 32-bit string, like formatting a barcode to always be the same width. This line reverses the 32-bit string. We wrap S in a string builder. Call reverse to flip the entire sequence of bits. And convert it back into a normal string called R. So the leftmost bit becomes the rightmost, and vice versa, a complete mirror image of the original bit pattern. Now we convert the reversed binary string back into a number. Long.parse long R, 2, reads the string as a base 2 number. We cast it down to an int since we know the value fits in 32 bits after reversing. This final integer is the result of reversing all the bits of n. And that's how this algorithm works. It first initializes an empty result, then repeatedly extracts the last bit of the input number and shifts it into the reversed output until all 32 bits have been processed. Efficient, simple, and elegant. Solution 2. Test case 2. Let's test our function using this input. 2,147,483,644. This number represents a 32-bit integer whose full binary pattern we want to reverse from left to right, flipping every bit position. Here's why the solution works. We first convert the number into a 32-bit binary string, padding with leading zeros so every bit is represented. Then we reverse that entire string, meaning the most significant bit becomes the least significant bit and vice versa. Finally, we parse that reversed binary string back into a numeric value. For 2,147,483,644, the binary ends with 2 zeros and begins with nearly all ones. Once reversed, those leading ones get moved to the right side, forming the new number, 1,073,741,822. And that's exactly what our program outputs, 1,073,741,822. And the expected result is also 1,073,741,822, confirming that the bit reversal logic executed perfectly. So, our implementation is correct. The algorithm successfully mirrors all 32 bits using clean string formatting and reversal, efficient, accurate, and reliable. Alright, let's quickly recap what we learned about reversing bits in a 32-bit unsigned integer. Breakdown recap. We started by understanding that the task is to flip the order of bits, turning the least significant bit into the most significant, and vice versa. Conceptually, it's like mirroring the binary pattern of the number. Assess recap. We realized that a simple loop-based approach works best here. There's no need for optimization tricks. Iterating through all 32 bits is already efficient since the bit count never changes. Structure recap. We built our logic step by step. Initialize a result, shift it left each time to make space, take the current bit from the original number, and move to the next bit by shifting right. Implement recap. We then implemented this logic directly in LeetCode, and the code ran smoothly without any syntax or logical issues. Check recap. Finally, we verified our result using LeetCode's test cases, confirming that our function correctly reversed the bits every single time. The key takeaway here is that sometimes the most direct approach, like looping through each bit, can be both clean and optimal. Bit manipulation problems often reward clarity over complexity.